Welcome back, candidates. In the previous module, we looked at hypothesis testing on a single population mean. What we're now going to do is look at differences in means. Now, two things we're going to look at here is differences in means and mean differences. They sound virtually identical, don't they? Difference in means and mean differences, but they're two very different tests, and we must be able to distinguish between the two of them. Okay, so here is our differences in means and mean difference. Let's focus on the LOS here. It says, for both differences in means and mean differences, identify the appropriate test statistic and interpret the results for a hypothesis test. What it doesn't appear that we'll be doing is actually calculating the test statistic itself. Now, in terms of testing, it's the same old testing we've done before. We're going to always reject our test statistics if they are greater than the critical value, because that means we're in the tails of our test. So reject the t-stat if it's greater than the critical value or less than the negative critical value, if we're doing two-tailed testing, of course. So again, test statistic in the tail of a test, reject. No difference from when we're looking at a single mean. But we've got two tests here. First, difference in means, and secondly, mean differences. Let's have a look at difference in means first of all. So it's a test for samples from two independent populations. Okay, independent populations. So maybe I've got two portfolios. One, a value-based portfolio, and one, a growth portfolio. And I want to test, are their mean returns the same or different? Well, that is difference in means, because I've got two independent populations, my value-based portfolio and my growth-based portfolio. Now, mean differences is quite different, and in particular, it talks about dependent. So what will we use mean differences for? Well, maybe I'm looking at some companies and there's been a regulatory change in the marketplace, and I want to test, has that affected the mean PE ratio? So what I would do is I would pick my sample, okay, and calculate their PE ratio before the regulatory change. I would then pick the same sample, and that's where we get the phrase dependent. So the same companies after the regulatory change, and I would look at their mean PE ratio then. Okay, so key point, I've got the same observations in each of my samples. The same companies before the regulatory change and after the regulatory change. That therefore is referred to as being dependent. With my difference in means, it was very different. I was looking at value stocks and growth stocks, okay, and hypothesizing that they may have the same or different means. Right, okay, so it's independent and dependent that are our critical words on this slide. So let's have a look at our test statistic for difference in means. So we're testing whether the means of two normal populations are equal. So I want to test, do value stocks have the same mean return as growth stocks? Okay, so they are independent samples because I'm picking one sample from the growth stocks and one sample from the value stocks, hence independent. Now we're assuming that they have the same level of risk, so variances are assumed to be equal. Do you have to assume variances are equal? Well, in the real world, no, but that's just not in our syllabus at level 1. We are only asked about this assuming variances are equal. Well, let's have a look at our test statistic. Look, we're looking at the mean return on sample 1, and that's let's say that's our value-based portfolios, minus our mean return on sample 2, and let's say that's come from the growth stocks. So sample 1 has come from value stocks, sample 1 has come from growth stocks, and I'm just looking at the difference between them. And then, as per normal, I'm putting them over a measure of standard error. Okay, now in order to calculate this, it looks a bit weird, doesn't it? It says SP squared. Now SP is our pooled standard deviation or pooled variance estimator if we square it. Okay, remember we're assuming that both samples come from populations that have the same variance in this case. Okay, let's get straight into an example and see if we can put some light into this. So here we've got two different populations. One is companies that have undergone horizontal mergers, Okay, and the other population is companies that have undergone vertical mergers. So horizontal mergers, remember, means mergers between competitors, and vertical mergers means mergers between suppliers and producers, or distributors and producers, that kind of stuff. Okay, so with our horizontal merger, we've got a mean on our sample of 1% and a standard deviation of 1%. And on our vertical mergers, we've got a mean of 2.5 and a standard deviation of 2%. We're going to assume these samples are independent, i.e. the same companies aren't in both of our samples. The degrees of freedom here are 120, so we've got 120 degrees of freedom. Significance level is 5%, and the calculated t-stat is minus 5.474. Determine whether abnormal returns are the same for horizontal and vertical mergers. Okay, so there's our null hypothesis. Our null hypothesis is that the two populations, okay, so horizontal mergers and vertical mergers, the difference between their mean returns is 0, their abnormal returns is 0, and the alternative is the difference in their abnormal returns is not equal to 0. Okay, so we need to look up the significance for our two-tailed test. Well, here's an extract of our student's t-distribution. We've got 120 degrees of freedom, 5% 5% significance, so 95% confidence. So we would look up the value 1.98. Now, of course, it's just a matter of comparing our t-stat to our critical value. Okay, now, of course, we're going to reject our null hypothesis here because our test stat of minus 5.474 standard errors, okay, that, of course, is beyond the minus 1.98. So we are firmly in the left-hand tail, and therefore we reject the null. And we're therefore going to conclude that horizontal and vertical mergers have different abnormal returns. Okay, so now we turn our attention to mean difference. And the key point is we now have dependent samples. So the same observations are picked in the first sample and the second sample. Remember, we tend to use these when we think there's been some kind of change taken place and we want to know, has that affected our means? Okay, so we look at the mean of the sample differences. So in other words, let's say we're looking at a company, some companies before and after a regulatory change in their market. We would look at their mean returns before the regulatory change and compare that to the mean returns after the regulatory change. And it's those differences in returns that is the mean of the sample differences. Okay, so in other words, a company's return before the regulatory change and a company's return after the regulatory change. We then compare that to our hypothesized value, and often we choose 0 here. Why? Because we're saying let's assume that the regulatory change has not affected the company's mean returns or price earnings ratio or whatever we're looking at. Okay. Our standard deviation, it's the standard deviation of the sample differences, okay, over the square root of n. In other words, the standard deviation of the differences in mean before and after the regulatory change over the square root of n. Okay, so an analyst is examining estimated betas in an industry before and after deregulation. Betas may have increased or decreased. The analyst calculates a t-stat of 10.26 based on a sample size of 39 firms. Now again, remember, when you're calculating that, you're looking at the same 39 firms before the regulatory change and the same 39 firms after the regulatory change. It is dependent samples. We're using a 5% significance, determine whether there was a change in betas caused by the deregulation. Okay, so our null hypothesis is that there is no change in the betas before and after regulation. The alternative is that there was a change before and after the regulation. Okay, so we're going to look up degrees of freedom. We look up 38 degrees of freedom. Okay, notice we've got 5% significance again, so 95% confidence, and we're using degrees of freedom here of 38. So again, we're going to reject our null hypothesis because our test stat gave us 10.26 standard errors, and yet the tail starts at 2.024 standard errors. So we are well inside the right-hand tail here. So reject the null, and we therefore conclude that the regulatory change, i.e. deregulation, has caused a change in companies' betas.